Hi everyone. Sorry, I just got us started. I finished up small groups, so quickly get myself over here to this Zoom. But welcome everyone. Welcome to day two of AP Calc. Let me get my attendance thing ready. While I'm doing that, if you haven't yet, please make sure you go to Google Classroom. I just put up these slides so that you can copy and follow along. So let me just log in. Welcome, everyone that's coming in. Wow, we're getting a bunch of us. Oh, glad we have a lot of folks here. All right, cool. Let's go ahead and jump into our check-in so we can see who we have. All right, so it is April 12th, everyone. Welcome to AB Calc. Um, okay, so today's check-in question is, what's something, and it could be like anything, something small, something you could do today that would be good for you? Go ahead and think about that something and put it there into the chat. And okay, great. Yeah, I can take a nap. For me, naps, it's like if I take a nap, it's going to be a 3 hour nap. Otherwise, I don't know. I don't know how people can do short naps. We got read. Yes, I love reading. I love getting lost in a book. I need to do that more often. We got get more sleep, finish an assignment, go for a run. Oh, that's nice. Going for a run. I miss that. I actually miss like when like I would usually take the BART to go to work. So I miss like that exercise I would just get from doing a lot of walking. Um and that fresh air in the morning. Wasn't so great in the hot days though, but we got finished assignments, go on a walk, do my work, we got some nap, and then procrastinate. So yeah, maybe for some of us, it do us a little bit of good to just, take a pause, maybe procrastinate on doing our things. That's also legit. All right, let's see who we have here, y'all. Um, Let me just double check who we're missing, who we have. Sorry, I was too into this check-in that I definitely need to make sure that I'm being extra careful when I take attendance. Don't worry, I'm gonna see who we're missing here. Okay, I think I got it, y'all. Okay, so this is who we're missing here today. We're missing just two folks, Shannon and Grecia. So if you're friends with either Shannon or Grecia, let them know to come on into class. And yeah, but I'm glad that most of us are here. Yay. Oh, we have another one. What will be something that will be good for us? We have be productive. Yeah, I think it's great to have Monday. Like looking at Monday is like if you start Monday productively, maybe the rest of the week could probably go on more productive as well. Like setting the start or the tone like productive. Totally, I could totally see that happening. Okay, y'all. Thank you so much. I appreciate y'all sharing in this check-in. Let's jump into today's stuff. Again, as a reminder, our slides are on Google Classroom. So double check that there so you can follow along. Here's our agenda, y'all. So we just took attendance. Um, the other time we kind of started off talking about antiderivatives. We're going to be finishing that up today. And I think your first asynchronous assignment was getting a little bit of practice on antiderivatives. We're going to have a review about Riemann sums once we're done with the antiderivative portion. So maybe you're like, what in the world's Riemann sums? Don't worry, we'll recover it. So don't be afraid. Then we'll have our checkout. And then lastly, asynchronous number 7, the next asynchronous, that one's due on Wednesday. So it's Monday today. So your next one is due Wednesday. And it's more so once we kind of cover the Riemann sum part again. Let me know if anyone has any questions about our agenda here today. All right, awesome. Let's go ahead and get us started. So let's jump back into our stuff. But actually, before jumping in, I like to do recaps. So we're not, just jumping into cold water without a little bit of practice. That's how I like to look at it. Yeah. So last time when we were here, we talked, we refreshed about the derivative, and we talked about the different meanings of the derivative, like how it represents the slope of a function, how it gives us, you could visually see it as a tangent line to a curve. I also reviewed with you that power rule where you bring down the exponent, multiply, so forth. That's how you take the derivative. And then I also review with you how y'all used it in a past mini final. So we refreshed on what the derivative was. The next thing we did last time was we talked about this essential question that's going to drive this whole unit. The fact that the area under a rate graph, so if I was to shade this area here, right, the area would be 50 times 3, which is equivalent to my total distance. But we also saw that if I take the slope of this line right here, that gives me my rate. So there's like a weird cyclical nature happening, or a weird connection between a rate graph and what we call on the right an accumulation graph. So there is this cyclical nature, and we're going to be studying this, and it's going to drive us this unit. So that's something we talked about last time, and I'm going to keep kind of bringing up this image up so we could make those connections in our brains. Last but not least, we ended class last time figuring out what an antiderivative was, and how we kind of introduced this as I had you all think about, well, what can be replacing the red question mark? And basically, kind of with trial and error, we were able to figure out that the derivative of x, the derivative of x squared gives me 2x. And this question mark is basically your antiderivative. For this one, it took us a little bit more practice, but I believe we got this as our antiderivative, 1.5 x squared. And how you test that out, like testing if your antiderivative is indeed your antiderivative, is you check it by taking the derivative of your antiderivative. So what I mean by that is you bring this 2 down, subtract by 1. Oops. Sorry, we got Shannon coming. That's why my marker went away. You get this, which is of course equivalent to just 2x, so checkmate. This one, when you check it, bring down the 2. 2 times 1.5 is indeed 3, and then 2 minus 1 is just 1, which indeed gets you this. So you can check your antiderivative to make sure it does give you an answer to the derivative, if that makes sense. So we kind of talked a little bit about this last week. We're going to go ahead and finish up our discussion on antiderivatives and also get a rule so that you can easily find the antiderivative of any function with a power. So that was our little recap. Let me know if anyone has questions on that recap. Okay, and if there's no questions on recap, let's go on to continue our talk on the antiderivative. We are on slide 5, everyone. So the antiderivative, our learning target will continue to be, I can investigate and define the antiderivative. Again, I don't know, I keep adding a little dash there, but I believe you can write it without the dash. I've seen it both ways, but you might see it written like this or together like you see in the title. But here's our learning target. Let's go ahead and read that, make sure we prepare ourselves for this learning target. So again, we're coming in with an open mind. We're going to be investigating the antiderivative, and then we're going to be preparing to actually define what it is, and actually get a little shortcut as well. Okay, so first thing that I'm going to show you is this. We're going to be having a Padlet check though. After we get a little bit of investigation, we're doing this investigation actually as a whole class. It's not like a groups thing, not today, but right now this is as a whole class. Let me first actually have you take a look at any patterns you might see here. So what I have for you are in this table, let me just color it. This right here is a function. So I just wrote down common functions, common power functions. Like basically you have your constant one, you have your x squared function, you have your x cubed or x to the third function, and then you have your x to the fourth. Then what I did is I included another table where I put what the antiderivative of the function was. And I wanted to see if y'all can notice any patterns that you could hold on to, and then kind of put whatever pattern you see once our Padlet comes up. But just for the moment, just go ahead and take a look at this table, process any patterns you might see. And then we're gonna synthesize that. Okay, and we already, there's a notice of a pattern that's already here in the chat. Let me write it out here so y'all can see that. But you could also put this on the Padlet once it's time, but I just want to write it. The root is always one more in the antiderivative is something that was mentioned there privately in the chat as a kind of like a little notice about the pattern here. So I definitely see the one more that we're talking about. Like this is 2 and then it's 3, 3, 4, 4. So it's always one more, and the antiderivative was something that was noticed right here. Cool, cool. But for the moment, everyone else, go ahead and just take a look. I'll pause here. Oh, okay, we have another notice I'm going to write down as well. One is always being divided. That's another notice in the antiderivative, right? So right here, like 1 divided by 1 divided by 1 divided by. I mean, accepting this first one, right? Other than that, I do see that pattern. Or you could think of this as like 1 divided by 1 or something. So perhaps that can still work for all of them. Okay, and then again, this is, you don't have to add anything at this moment, but if you'd like to, I'm just going ahead and just taking little notes on what y'all are noticing about any patterns, because we're going to be using these patterns that we see here to come up with a rule that's going to help us find antiderivatives easier or more better for us instead of like guessing and checking, because guessing and checking does take time. So there is a formula we can use, and this is just kind of giving you a general exposure of perhaps you're able to kind of come up with a formula as you're looking at this. Okay, great. So I just definitely want to give time for anyone else who's still processing any patterns. I'm going to move us on. Thank you so much for those who contributed. Make sure if you want to, once it's Padlet time, you could also bring these same things back up as well. I'm going to go ahead and move us on to the next slide. So I have something else for you to investigate antiderivatives. Maybe you're more of a visual graph learner, which I know some of you are. Some of you like to use like Desmos and stuff to kind of make connections, but here's another tool. So I'm on slide number 7. So you could totally click on this with me on slide 7. Let me also just go ahead and put this in the chat if you'd like to explore this on your own as well. So here's another tool. Let me explain how this tool works. There's a tool if you'd like to explore it. Let me explain it. So for the moment, let's just ignore the writings. If you want to read the writings to make sense of it, you could totally do that. But what I have in red is the original function. So let me explain how this tool works. So red is just your original function. And in blue down here, what you see in blue is the antiderivative function. So for the moment, You can take a look at what's here, right? These like there's like a you've seen this symbol if you were in pre-calculus with me last year before. Perhaps you remember a little bit about it, that elongated S symbol, right? But in blue is your antiderivative, in red is your original function. Right now where it's set to is that the original function is 2x, and in blue, the antiderivative looks like a parabola. I can change my original function to be actually anything I want. So let's say I want my function to be, the original to be x squared. When my original function in red is x squared, take a look at how my antiderivative in blue is. So right now you're just, you could play around with this tool and just make any connections. Right now we're just investigating and we're having an open mind right now, just taking a look. I'm going to try to now go ahead and put my original function as x to the cubed. Let's see what happens. So in red is my original function, that's x to the cubed. And in blue, it kind of looks like a wide, flat at the bottom kind of parabola in blue. And we could play around with a different function. Let me see if I do something weird like e to the x powered. That's interesting. So if I do e to the x, the red function, its antiderivative is, it looks like the same thing, but shifted down. So that was weird. So see how you could just put any original function you want with this tool and it'll give you the antiderivative. What if my original function is a constant, like 2? So if my original function is a constant, a horizontal line at 2, my antiderivative appears to be a line, and it looks like it's a line with a slope of 2, actually, is what you see in blue here. So let me know if anyone would like me to try anything else, but this is just to kind of get you to make some connections with original function and antiderivative if you see any. Maybe right now it's all jumbled, that's okay. This is just an exploration. And again, you have the tool that you could check out too. Okay, try 7 to the third power, which is basically a constant, I think. What's 7 to the third? 7 times 3 times 3. 7 times itself 3 times. So that's why is 7 to the third look like that? 7 to the third, what is that? 7, okay, 7 to the third, that's 7 times 7 times 7, 3 times. What is that number? It's a large number, I think that's why. It's 343. So that means I can already, so that means I just need to zoom out. Where's my red? There you go. See that? My original function is a constant, 343. The blue line is actually a line with a slope of 343. That's why it looks like a straight up line, but it's not. It just has a really high slope and it looks vertical. That one was cool. That was an awesome suggestion, Juan. But that one is another example of a constant function. So yeah, so maybe you've made some connections right now as we're playing around with this tool. Again, you could even go basic, like what if I said my original function is x, and there's my, in blue, my antiderivative. So this is just a little whole class exploration. Let's see if anyone has any burning functions we should try to kind of investigate here. Okay, if not, let's go ahead and close up this investigation. So what I've showed you so far is I showed you a table with patterns, and I also gave you this Desmos tool that helps you kind of graph original functions and the antiderivative functions to kind of like explore there. So I gave you 2 things to take a look at. Let me clear up my screen now. And from these 2 tools that I gave you and we played around with, let's try to kind of put together what's in our minds now onto a Padlet. So what do you know / guess so far right now about the antiderivative? You could reference the table of patterns. You could reference that Desmos thing. You could even reference last week when we started talking about it. Let me go ahead and give everyone the Padlet. It's also on slide number 8 if you're there with us. And this is going to be our first participation check for day 2. And don't worry, I'll make sure I give your daily credits onto Power School so that, you're getting your in-class credits. So we are on column number 3 right now. So what do you know right now or guess right now about the antiderivatives, given the tools I kind of shared with y'all, the tables, tools, things like that? I'm going to go ahead and put the directions back in the chat to make sure we all know what we're doing right now. All right, and let's check in about a minute or two, y'all. All right, everyone. Sorry, don't mind the color coding. So I'm color coding usually when just to kind of get commonalities of things that are coming up, repetitively, and or if it's new. So I color code if your comment got color coded, it's because I want to just point out as it's a common answer or response. So we could talk a little bit about it. So basically I colored everything that was popping up or new. So something that was new, and by the way, if you're still adding your comment, please do. You can still write in your comment there. Something that was new, as a new thing that came up here, was I think the antiderivative is sort of like a reflection of derivatives. It's basically the same point, but like shifted, like vertically or horizontally. It seems like a fraction or some portion of the original derivative. Um, the next one, a lot of you mentioned patterns. So it follows a pattern, maybe based on the derivative, was something that was mentioned. And again, I highlighted this because that was mentioned more than once. So also are seeing patterns. The mention of the root is always one more in the antiderivative. That was the pattern that was noticed earlier. Then here was a new idea about what the antiderivative is. It's going to show us info that's different from the derivative, but it's also relevant and related. That's interesting. And then we have here another new idea. I think the antiderivative is the outcome graph of an OG function. And you see that reflection of derivative coming up. It did come up. Let me go back up because I saw something new happening right here in Shannon's comment. So I see that the antiderivative rule is this. So there's this rule or the pattern that's happening. I know it makes sense. And then there's some further thoughts. I'm going to highlight this too because this is new. So there is like a formula that is being seen here for this particular student. I think I couldn't highlight it because they're still typing, but yeah. So definitely, so there's a formula. Oops, there. I'm not gonna mess with that comment. All right, so thank you so much, y'all, for sharing your beautiful thoughts. Again, feel free to add in your comment if you haven't yet. Either put your name or initial. Let's go ahead. Oh, thank you, thank you. You all can color code your own comment. I appreciate it. Okay, and then it says it makes sense for the antiderivative to be fractionalized. So interesting. Let's go ahead and jump back into our slides, everyone. And let's learn, well, what is the antiderivative and what is the formula that was kind of mentioned there? I am on slide number 9. So this is our note portion. So feel free, like on your own copy, to just make little, annotations if it helps you. But let's go ahead and have some information now after our little investigations. The antiderivative. First thing. So the antiderivative is actually exactly what it sounds like. The antiderivative is the reverse of the derivative. That's exactly what we're doing when we're doing an antiderivative. Let's talk about some examples. So the derivative of x squared, if you do the power rule, is 2x. So we know that first part from prior modules. The derivative of x squared is 2x. Bring down the power, subtract 1. That means the antiderivative, so if I were to go backwards, reverse, right? That means that the antiderivative of 2x is x squared. So that's how we're kind of using the language. So if I go backwards, that is my antiderivative. I'm just going to put antider. Hope y'all know what my little annotation means. I could not write down the whole word. So that's just a little example, right? Next. What if we consider the derivative of x squared plus 2? Well, we know if we were to follow the regular derivative rules, right? You bring down the power and subtract by 1. You would get 2x to the first power. But then first power is just written as x. So I don't have to write to the first power. You would just get 2x. And then the derivative of a constant is 0 by definition. So then we have 2x plus 0, which is simply also 2x. So we have the derivative of this other function, x squared plus 2, is also just 2x. So then the antiderivative of 2x is also x squared plus 2 and x squared. Do you all see how the antiderivative of 2x has more than one thing? It's this and also this. And I bet you could come up with even more antiderivatives of 2x, right? So what the main point is here is that the antiderivative isn't unique. You can actually find a lot of antiderivatives for one function, actually. So we're going to be generalizing this as a rule later. So I don't know if y'all remember Shannon's comment when we saw the palette, there was a plus C. That's the generalization that we're talking about. But we're going to see that soon in a second. Does anyone have any questions so far about this slide, number 9? About antiderivatives and kind of finding out that you can have more than one antiderivative for many different functions. All right, if a question pops up, feel free, and I'm happy to go back and address it. So let's move on from slide 9 and let's transition to slide 10, y'all. Dun-dun-dun, there's the rule, y'all. The antiderivative power rule. Now, I know as you're looking at this, there's kind of some new notation, right? There's this symbol. Does anyone remember what this is called? Probably, I don't know if y'all remember or not, but there is a new symbol. New symbol as far as calculus right now. Yep, you have a new symbol. You also have this dx happening right here. Dx, we'll just put question mark. What is that? But basically what this formula is telling us is if you want to find the antiderivative of some x to the nth power, here's the rule. And some of you notice the fact that in the antiderivative, you were adding by 1 or increasing by 1. Y'all remember that's that portion right here that you see. You're increasing by 1 and you also have that division, the 1 over blah, that's right here. That represents the same thing. This plus c is the generalization I was talking about because there's more than one antiderivative for one function. In order to encompass all of them, you have to add plus c at the end of it. This is the rule, and we're going to get some practice in the next slide on how to use this rule. That way we don't have to guess and check no more. Again, for now, this symbol, let's go ahead and treat it as it representing find the antiderivative of. So let's just take this new symbol to be find the antiderivative for now. Antiderivative. Later, we're going to know a little bit more deeper about what this symbol represents really. But for now, let's just look at it as representing, telling us to kind of take the antiderivative of something. I'll pause here on this rule. Let's see if there's questions. I added in a little note there for that plus c. Again, the reason there's plus c in the rule is, again, because there's more than just one antiderivative for a function. So I want to make sure that's, if you're making some annotations on your slide, do make sure you include that if you are curious about the plus c in the rule. Plus c basically represents plus constant. C could be any constant. It's kind of like a little placeholder. Okay, let's go ahead and just put this rule into practice. So let's do this. Let's find some antiderivatives. Oh, goodness. Let's see. So I'm going to write the rule somewhere on my page right now. I'm just going to put it right here. So if I have some x to the n, I know that the antiderivative is going to be x to the n plus 1. And then I'm going to divide it by n plus 1. And then I have to put plus c at the end of it. I'm going to just shorthand this. So the antiderivative of something, here's the rule. And I know there was a little dx in the formula, but there we go. Okay, so now I'm looking at this. Okay, so first off, it has to be in this format where it's x to the nth power. So the 2 I'm going to kind of just disregard for the moment. I know that x is also known as x to the first power. So here's my power. Now I'm going to take the antiderivative of the variable while just at the moment ignoring that 2 in the front. So the antiderivative of x to the 1 is simply going to be x to the 1 plus 1 divided by 1 plus 1. Let's do it. I'm just applying that rule straight up. Divided by 1 plus 1. And I can't forget about my plus c. Now, once I've taken this antiderivative, I'm going to go ahead and bring my 2 down in front like this. Now all we have to do is simplify it. 1 plus 1 is 2. So I'm going to rewrite this as 2 divided by 2 plus c. Now, yeah, I have this expression written like this, and I'm going to ask you all, is there any way I could kind of simplify anything that's here? Let's see if anyone has any ideas in the chat. Like I mean, I wouldn't mark you wrong if you wrote your antiderivative like that. It's correct, but we could simplify it. Then we have the 2. Yes, that 2 that you all see there. Thank you, Edgar. Let me change my color. 1 second. Let me get out of the chat. Okay, there we go. So y'all see this 2 and the 2? Basically, this is like 2 divided by 2, which is 1. You can cancel this out. And then, therefore, our antiderivative in simplified form is simply going to be x squared plus c. That is the antiderivative of 2x. It's x squared plus c, and c represents any constant. And again, I know I was addressing, I still remember your question, and this is Sophia P's question. When you asked, what about the constant? That's how we take care of it, is adding the plus c. So that was a great question. So there's our answer there in red. And then right here, my annotations is kind of how I did it step by step using the formula. Let's see if there's questions about example 1. Okay, so far I don't see questions. Again, feel free to even ask it privately if in case, you don't want to ask it publicly. I totally understand as well, and I could totally address your question. So that was example 1. Awesome. Let's go on and see another example. Let's continue practicing. So in order to do this other one, let me delete this so that I have space to kind of write. So I'm going to delete my work. Delete this except for the formula. Okay, so this is nice. This one's nice because I don't have a constant in front, so I could directly just apply the power rule right here. The power rule for antiderivatives is what I mean when I say that now. So I'm using this rule. So great, I have x to the n, except n in this case is 2. So then in order to find the antiderivative, I'm going to do 2 plus 1 divided by 2 plus 1. So the antiderivative of this is going to be x to the 2 plus 1 divided by 2 plus 1. And we got that plus c. Don't forget about that plus c, y'all. In the AP exam, they add the plus c. And if you forget the plus c, they minus points. So don't forget about the plus c when you're finding antiderivatives. So this is just going to become x to the 3rd divided by 3. And we got plus c. That is, I think that's as far as we could simplify this. And we are done. This is our antiderivative. And notice how I've written it like this, right, y'all? You can equivalently write it like this, where you have the 1/3 out in the front. That means the same thing as what I have here. Both of these are equivalent expressions. So let me just pause, see if there's questions. If not, we'll do 2 more examples. Sorry. All right, in these last 2 examples, everyone, I went ahead and put in that symbol. With just the idea that this symbol basically means the same thing that's written up here. Find the antiderivative of this function. The dx right here means with respect to the variable x. Sometimes you have different variables, so that's why we write dx. We're going to learn a little bit more about the dx later, though, and what it means. But for now, let's find the antiderivative of x to the 7th. So I'm going to just go ahead and apply the rule. If you want me to write it out step by step as I've been doing, please advocate for that in the chat. You could do it in a private chat. I'm happy to do that. But I'm going to just directly look at this and be like, okay, that's x to the 8 divided by 8 plus c. There's my antiderivative. So instead of you doing guessing and checking about what the antiderivative could possibly be, this rule gives you a quicker method to find the antiderivative. instead of, guessing and checking. So that's example 3. Let me know if there's questions. Okay, okay. Last one, example 4. So again, if you're able to do this on your own, that's awesome. This is the last one here. If you have x to the 6th, again, I'm just looking up at the rule. All I got to do is add 1, make sure I divide, add my plus c, and I'm done. That's my antiderivative, and it's right here. You should have 1/7 x to the 7th plus c. There we go. So there are our 4 different examples on how to apply the power rule for antiderivatives. Remember, there's the power rule for derivatives. That's when you bring that, that's the opposite, right? So make sure you don't mix up your rules. But this is the power rule for antiderivatives. This is what we're doing at the moment. All right, all right. Let me go ahead and move us on to the next slide, y'all. So I'm going to go on to slide number 12. And I'm bringing back this question. We're going to, soon, everyone, we're going to be jumping into a Padlet. But I'm, again, bringing this back. Again, this picture holds the fundamental theorem of calculus. And that's why I keep going back to it, because it's a very simple picture. Like I like the basic graphs, and the basicness of it will help us understand the complex theorem later on when we hit it. So again, I'm going to just show you the connections once more. So again, I'm going to shade the area under my rate graph. This is my rate, because speed is a rate. When you have miles per hour, that's a rate. You have different rates in the real world. There's miles per hour, there's gallons per minute, there's different kinds of rates that, you experience. When you experience every day is driving in a car, speed is a rate. So I'm just shading in this area. And let me just change my color. Again, the area under a rate graph, this is a rate. The area of the shaded region, it's 50, the height of the rectangle, it's 50 miles per hour times the base of the rectangle. This is my base, 3 hours. When you multiply these two, right? First off, there's some units that are canceling. So this is kind of getting deeper into the specifics. So hours will cancel out when you multiply these two units. When you multiply the rate times the time, you get your remaining unit. In this case, see how that's how we get our distance, which is miles. So when you multiply these out, you get 50 times 3, which is 150 miles. And it isn't a coincidence that this area, the area under the rate graph, is giving you the total distance after 3 hours that you're on the whatever, driving or something. Total distance after 3 hours, 150. So again, area under the rate graph gives me total accumulation. Remember, accumulation just means whatever is getting accumulated. In this case, it's distance. Because sometimes the thing that's getting accumulated is not always distance. So that's why we call it total accumulation. And then the other part of it was, but if I find the slope of this, so rise over run, so my rise is 150. I go up by 150 miles, and my run, 3 hours. If I do this division, 150 divided by 3, that gives me 50 miles per hour. And this is my rate, 50, the constant rate, 50 miles per hour. And let me just type out what I just did. When I find the slope of the accumulation graph, I get my rate. Why am I bringing this back? It's important again, and also it's going to lead us into the next Padlet check. And again, it's super important to just make sure we solidify how these two graphs are connected because it's going to relate to the fundamental theorem of calculus. So feel free to like take a picture or something on your phone or something if you need to, because I'm going to keep showing this this here back to us throughout this module. Let's transition to the next slide so y'all know what's on our Padlet. Oh wait, there's something in the chat. Will this recording be on Classroom? On Remind. Wait, do y'all want it on Classroom? Because I could also upload it on Classroom. Let me just see if I know I have like 12 of you on my Remind, but yes, I do have the recordings. I also have the last one. If you need it on Classroom, yes, I've usually been sending it. Okay, so yes, Classroom. Okay, what I could do is I should leave the videos as a comment right below the slides. I'll do that. Okay, so I'll add it to the Classroom as well. Let's do that. Yes, we'll do that. Okay, so I'm gonna go ahead and clear the screen. I know I talked about this connection, but I'm doing it once more, but this time I did it in more detail. With kind of like actually canceling out and things like that. Okay, y'all. So right now what I showed you is when we found the area under the rate graph, it was nice because it was a rectangle. The area under that rectangle was equal to the distance. That was nice. But what if your rate graph is not a rectangle? What if the area is something like curvy like this right here? Look at this curvy rate graph. Now this is a rate because this is actually heart rate in beats per minute. So this is a rate. What are you supposed to do when you're trying to find the area under something that's curvy? Like what if I want to know the total beats? Because if I was to find the area under this curve, it would give me the beats, how many beats in total that the heart made. But how would I do that? What do I do if I have a curvy rate graph is my question. How will we find this accumulated unit, which is in this case beats? Here's my beats. It's beats per minute. So I would just shorthand that to bits or something, beats per min. If you were to, again, if you multiply it by its base down here, y'all, is minutes. So again, it's all about unit canceling. But if you were to multiply by the minutes, again, the thing that's canceling is minutes. And the thing that's getting accumulated, if you were to find the area under the curve, is beats. BTS for beats. But anyways, that's just what the area under this specific curve represents. For the moment, we're going to be going onto a Padlet now. And we're going to try to think about how in the world can we find the area under a curvy rate graph? How will we determine the accumulated unit? What are some strategies that you can remember or that you could just think up right now as we're thinking about this? This is a Padlet. Let me clear this up. And the Padlet is in the, it's actually in it's on the slide. And it's the same Padlet. I'm just going to go ahead and put it back in case you don't have it, but it's in our slide down here if you're following along. I want to see some ideas. Like, what can we do if I have a curvy rate graph? What if it's not nice, like the way it was when we made the connection, like a rectangle? We are on column number 4, everyone. What do we do when we have a curvy graph? I'm going to put the directions in the chat, and then we'll check in to see your ideas. And we're on column 4. Let's check in about a minute, y'all. I already see some ideas popping in. And it's also okay if you don't know. You could put a notice or wonder. It's any idea that's coming up for you and what you could do to tackle, like if you have something that's curvy, like this picture here. All right, I'll see y'all in about a minute. Hey everyone, I'm going to go ahead and give you all some more time. We still have some more thoughts populating, so let's have another minute and then we'll come back. Okay, everyone, welcome back. Definitely want to give you time to process your thoughts on this. But let's see what's coming up for us. So, some ideas, and it came up more than once, was creating a function to kind of model the area. I guess finding an area function is what was an idea that was coming up. Another thing that came up, some of you remembered a process we did last year. I think I saw another post that said something about we did last year. Another idea is to kind of like see what the first last number is and then see the difference between maybe something in the middle to make an estimate is what I see happening here. Awesome. And then there's that thing. So the thing from last year. So Edgar mentioned it. Sophia even adds to that. It looks like remembering left and right endpoint rectangles or something. So there's a little bit of remembrance of a certain process we did. And then there's a mention of a limit. So that one I find interesting. I'm going to definitely highlight that. So there might be limits involved. That's cool. Again, that creating a function, some are still processing our thoughts, and we could use other shapes. Like, I don't know, maybe that's exactly, yeah, you could also use other shapes. I don't know if y'all remember that also last year, we tried to estimate areas under curves by using other geometric shapes as well. Yes, those are all super valid. Again, if you're still processing your thoughts, oh, okay. I like that. So I remember cutting up the graph and adding up the area. So adding up the area is something kind of new that's coming up. So I'm going to highlight that too. So adding up the area is coming up. So yes, again, I'm highlighting new ones or things that are coming up. So if you already, if it's not highlighted, it's because I either didn't see it or it came up already. And then yes, so creating an equation that perhaps represents the area. Those are all amazing ideas. So we're gonna go ahead and transition, y'all. If you're curious, yes, it's gonna transition us into something we did do last year, and that's called Riemann sums. So we're gonna continue our discussion tomorrow about Riemann sums, and we're gonna review that tomorrow. But let's go ahead and go into our checkout for today very quickly to end our class. Just name something, one thing today that made sense. What's just one thing that made sense for you today? Let's put that into the chat. And it could be one word, and that's okay. It's like one thing that made sense for you. Okay, we have something that made sense. How to use the formula for antiderivatives. Oh, that's happening a lot. What how to find the formula, and then something that made sense is why there's multiple antiderivatives. Yes, that's like the plus C part. Love that. The equation, I'm assuming it could be the antiderivative equation. So the antiderivative function and how to solve plus. Awesome. I understand how to find the antiderivative. So I completely understand. Yes. So I love that. There's some learning happening here today, even though we're at a distance. So that's super powerful. How to use the power rule and keeping the plus C in there. Yes. Don't forget those plus C's. Definitely. Yes, everyone. Any last minute burning things of something that made sense today, here today for us all? Okay, I'm gonna go ahead and release you all to lunch. Y'all have a great lunch. Let's see each other tomorrow and continue our discussion. Bye, everyone. Great job. Bye. See ya.